What I'm going to do now that we've talked about how to design and implement a Memoizer, and we've talked about the Java Executor Completion Service class, I'm going to show you how you can implement a new version of the PrimeChecker app using both the Memoizer and the Executor Completion Service. Now, there's nothing really inherent with the Memoizer and Executor Completion Service. We could also use the Memoizer with any of the previous versions as well. But this is a good time to talk about all these different things coming together. So just a quick recap. You probably remember this by now because we've talked about it multiple times. But basically the app that we're running here is going to check to see if n random numbers, randomly generated numbers, are prime, and it's got a GUI interface. You can download and run this app. It's really cool. And this particular one uses the Executor Completion Service and this modern Java Memoizer. The app is embarrassingly parallel, which means there's no dependencies between checking if different numbers are prime, and it's compute bound, which means that the prime check operation will not require any I/O. And because the prime check operation is a long-running, expensive call, especially on large random numbers, that's why we're going to use the Memoizer in order to cache those results so we can speed the lookups considerably. So here's a bit more implementation detail for this particular version. Unlike the previous implementations of the PrimeChecker app, which used fixed size thread pools, this time, just for kicks, we're going to use a new cache thread pool. And as you'll see, the only real change is where we create the executor. Before we used the new fixed thread pool factory method, now we're going to use the new cached thread pool factory method. But nothing else changes because, of course, that's the whole purpose of the executor framework, is to make it easy to plug and play different thread pool implementations without breaking client code that uses it. So we have this cache thread pool that will create threads. And if there's already a thread in the pool that's unused, the next call to execute something or submit something will go ahead and use that existing thread. Here's the way we are going to implement PrimeCallable. This is a little different from our previous version because now we're going to leverage the fact that we've got this Memoizer and the fact that the Memoizer is actually implemented using the functional interface. Just a quick recap on what PrimeCallable does. It defines a two-way means to determine whether a given number, which we call the prime candidate, is prime or not. And so you can see here that PrimeCallable implements callable. That's the same as before. It defines a field called PrimeChecker or mPrimeChecker, and that's going to allow us to parameterize the way in which we're going to do the prime checking function. And that's intentionally designed to be a function. And as you can see down here, we stash that away in the constructor. And then here's the call hook method, because of course, PrimeCallable implements callable. And the call hook method will be called back by a pool in the cache thread pool. And what it's going to do is it's first going to call the apply method on the function field. And that will, if we configure this to use the Memoizer, that will use the Memoizer to do it, where it'll look it up if it's already been computed. Otherwise, it'll compute it and add it to the cache. Otherwise, it'll just call the prime function if you don't configure this thing to use the Memoizer version. The result of all this stuff will come back as a prime result, and a prime result is just this kind of a tuple that keeps track of the prime number candidate and the results of calling the prime number check, which may or may not have occurred each time, depending on whether memoization is enabled or not. The main activity of this program will create a Memoizer that will be used to optimize the prime number checking of count random numbers. And here's kind of what this looks like. So you can see when someone clicks the start button to start the computations, as part of the initialization in the main activity, that will make a new Memoizer. And in this particular case, just for fun, we're going to use the brute force checker to burn a lot of CPU time. But you'll see it's absolutely trivial to change that to a more efficient checker that could be done more optimally if we so decided. And nothing else changes, which is cool. That's about behavior parameterization using method references. And so it's as simple as going from brute force to efficient. Boom, we're up and going because of behavior parameterization. This particular implementation also uses a concurrent hash map, and that's just to make sure that we have efficient thread-safe map operations. Here's the main body of the main activity. When you do the computations, we generate count random numbers in the range between S max value minus count and S max value, and that's done to ensure duplicates. We then take each of those random numbers that were generated and we make a PrimeCallable. If you recall, the constructor of PrimeCallable will basically go ahead and just initialize those fields. And then, and so what's nice about this is we can pass in the Memoizer, which will either be the Memoizer or just a regular call to the PrimeChecker brute force checker or the efficient checker and so on. So we can parameterize whether we want to do memoization trivially without breaking anything else in our code. And then the last thing we do is we take each of those PrimeCallables that we just created that wrap up the random numbers, the random number prime, the prime candidates, and then we submit them to the executor completion service. So for each of these callables, we go ahead and we will submit them. And that will basically put them all in the map, or that'll basically start the wheels turning. And the nice thing about this is there's no need to have a list of futures, which is how we had done it before when we did the executor service version, because all the stuff that's being handled here is going to be encapsulated by the executor completion service. So there, that completion queue that's needed internally for everything to work is done inside the executor completion service. We do, however, need another thread, and that thread is going to run in the background and basically wait for completed futures. And this is how it works. We make something called a completion runnable, and we make a new completion runnable. We make a new thread that will use the completion runnable, and then we start that background thread. Here's what completion runnable looks like. As you can see, it implements the runnable interface. So it's got a run hook method. It's got a constructor that stashes away the various information when it's created. And then, as you can see, it has a run hook method. This run hook method will be called in that background thread, and it'll iterate through all the results from 0 to M count. And every time through, it's going to call the take method on the executor completion service instance. And what that will do is take will block until there's at least one completed result ready, in which case it'll return that completed result. It comes back as a future, but of course that future has already been completed because of the way that the executor completion service works. And then the get call is invoked on that completed future to get the result. And then we do something to print out the results, whether or not they're prime or not, based on the result that comes back from the completed future. Another little sort of Androidism, we store all the state related to concurrency in this thing called the retain state class. So we put the executor completion service and the executor service and the completion runnable and the thread and the Memoizer. We stick all of that stuff in this retain state instance. And then that allows us to use a cool Android technique to be able to retain state across runtime reconfigurations as people move the phone from one orientation like portrait orientation to landscape orientation. That's kind of an Androidism thing, but it's a very clean way to keep computations running in the background while orientation changes are occurring. So that's the end of our discussion of the Java Executor Completion Service app. And hopefully this will be more clear and more powerful than the earlier versions we talked about. And we'll talk about that in a second when we evaluate everything that we just learned.